Hey everyone, we're going to work through our parallel circuit assignment on the Quest. Just like before, your numbers might be different from mine, kind of like the group quizzes where like you all have different numbers. But you can answer them in the same way. So if you're stuck on that problem, kind of keep watching and we'll see what we can do. Alright, question number 1. Consider a series combination of two resistances. What is the equivalent resistance? Okay, so we've got a series circuit. We know that for two different reasons. One is, I kind of told you, it's a series circuit. But also, it's worth pointing out that it's a series circuit because if you followed your straight line path in a loop around the circuit, it's a series circuit if you only have one path to take. So if I sort of follow along here, alright, I have to go through this resistor, I have to go through the other one, and now I'm back where I started. At no point did I have an option for which way to go, so we know that it's a series circuit. Even if I didn't, tell you the word series in the problem, you should be able to figure that one out anyway. And we want that equivalent resistance. Again, just another way of saying the total resistance. Alright, well, for a series circuit, I don't know, if you forget your rules, I forgot them, so I'm just going to check my circuit rules. Sorry, I have every tab in the world open right now. So, I'm going to check my series circuit rules, and it looks like to find that equivalent resistance of a series circuit, I think I can just kind of add them. I'm looking at this rule right here. So, that's what I'll do. I'm going to do 25 plus 30. Again, I'm just adding them because it's a series circuit. And 25 plus 30 is, I believe, 55, right? 25 plus 30. So, that's what I'm going to go with. Again, it's just 25 plus 30. I want to emphasize that I added them because it's a series circuit. Parallel circuits are a little different. So let's look at question 2. I'm trying to highlight the difference between these two. Consider a parallel combination. Okay, it's a parallel circuit, and you know that for two reasons. One is I told you that. I said it's a parallel circuit. Or, again, let's follow along here. It looks different than the ones I typically draw, but if you're following, let's say you're an electron, you get all your voltage out of the battery, you're like real excited because you got all this energy. You reach this point here and see you've got like sort of an option. You can go through this resistor, the 25, or you can go through the 30 ohm. That means that this is a parallel circuit. So again, I know I told you that in the problem, but it's worth pointing out. We know it's parallel because at this point right here we had a choice about which resistor to go through. I'm looking for what is the equivalent resistance. So we cannot just add them, because that's not how parallel circuits work. We have to go with that more complicated rule. So, for starters though, we also said that in the previous lesson, if you haven't watched it yet, please watch it. We said that if you add more paths for current to take, then it's easier for the current to move. Meaning, like, if we only had the 30 ohm resistor, that would be harder for current to go through. But if we add another path for it to take, it's a little bit easier. And I know that the 25 ohm resistor has a resistance to it, but the fact that we added more options means that the current has like more paths to take. It has more options. It's like adding more like lanes in a highway, right? If you have more lanes to go through, yeah, they all have their own resistances, but more lanes is better, right? You could move through it faster. So we know that the current should be larger. And if there's more current, that means that the total resistance is smaller. In fact, it should always be smaller than the smallest value. So the answer to this one is going to be less than 25 ohms. If you didn't like that, if that didn't make any sense to you, that we can actually do the math. So I'm going to work through all of that right now. For a parallel circuit, we can't just add them. We have to go with, let's look up that rule just in case we forgot. It's all in the reference table, so I'm going to keep referring back to this. For the parallel circuits, your rules are right here. I'm looking at this rule right here, that bottom row, that 1 over REQ equals 1 over R1 plus 1 over R2, and so on. So that's the one I'm going to use here. So we've got 1 over REQ, which is what we're finding, is equal to 1 over R1 plus 1 over R2. And we can stop there because I think there's only 2 resistors here. Let's plug in. I'm not going to show all of my units because, gotta be honest, I'm having a lot of trouble writing on this surface. 1 over 25 plus 1 over 30 is, again, 1 over REQ. So I'm going to throw that in a calculator, which I forgot to do ahead of time. Okay, so when I put that in the calculator, I got 1 over REQ. And again, I just plugged in 1 over 25 plus 1 over 30. I got that's a decimal, 0.73 repeating. Okay, but just like before, that's not the equivalent resistance. That's 1 over the equivalent resistance. So what I'm going to do about that is this. I'm going to put that whole thing over 1, and then I'm just going to flip both sides, which again is a mathematically sound thing to do. REQ over 1 is equal to 1 over 0.0733 repeating. I'm sorry, that's a 7. Okay, REQ over 1 is just REQ, the equivalent resistance. Just type in 1 over 0.073333 in your calculator, and I got 13.636 ohms. So to go back to the question, 13.636 is definitely less than 25. So, if you do the math, you should sort of arrive at that same answer. Okay. Number 3. All right, we got a 4-part question. As soon as I look at this, I'm looking at like multiple resistors here, right? And as soon as you see that, we know we're going to set up a VERP chart. So I'm going to do that. Alright. So first I'm going to draw it out because, again, I like drawing it out. I find it helpful. You don't have to. But if it helps you, then do it. So we've got, okay, looks like we've got 1, 2, 3 resistors. That's the 22, the 12, and the 6. All connected in parallel to, and I want to apologize, I don't think I used this word yet. An EMF source just means a voltage source. It stands for electromotive force. It's just a different word for voltage or potential difference. So we've got our EMF source, which again is just a voltage source. We've got 1 resistor, 2 resistors, we've got 3 resistors. I'm going to write in all their, and actually before I get too far, I already know this is going to be a VERP chart problem without really reading it, without really reading it because, I don't know, it's a circuit analysis, right? That's what we do for these circuit problems. That's a P, right everyone? Yeah, it's a P. Alright, we can find these values for the first resistor, or the second one, or the third one, or the circuit as a whole. So let's give that total its own row. And let's start filling in what we can, just like we did for the series circuits. We're just going to fill in like everything we can, and then we'll take the problem from there. So we know we've got this like a 22 ohm resistor, we've got a 12 ohm resistor, we've got a 6 ohm resistor. So they gave us kind of a weird set of information. We know that the current through the 12 ohm resistor is 5 amps. So like all that current, it goes through here, and it has a value of 5 amps. Filling that in our table here, we know that, okay, well, this has a value of 22. Sorry. I tried. 12. Second one has a value of 12. This one has a value of 6. And then, alright, a current of 5 amps is through the 12 ohm resistor. So that's this current here. And this has a value of 5. Again, I didn't show my units, which is bad, but I'm having trouble writing here. Alright, calculate the equivalent resistance, and if a high school student got this wrong, I would assume that you did 22 plus 12 plus 6, but that is wrong, because this is not a series circuit. Let's double check our rules for this parallel circuit, And it looks like we can't just... oh no, I just wrote a pen on my computer screen. Looks like we can't just add the resistances. I think we have to do this whole 1 over mess, so that's what I'm going to do. Alright, 1 over REQ is equal to 1 over 20. Oops, let's show the equation first. 1 over R1 plus 1 over R2 plus 1 over R3. Let's plug in some numbers here. 1 over REQ is equal to, I'm just going to plug in each of those resistances individually. So 1 over 22 plus 1 over 12 plus 1 over 6. Okay, again, I'm not going to do the common denominator for these numbers. It doesn't work out so clean. But if you add those all up in your calculator, what you get is, I got 1 over REQ is equal to, I got 0.29545, and again that's a decimal right there. For this problem, for Quest, it's not something I would take off points for on like a test or quiz, but for Quest I'm gonna recommend that you do not round here. And just like before, come on, nope. Just like before, we're not solving for 1 over REQ, we're solving for REQ. So I'm going to put this whole thing over 1 and then flip both sides. So flip REQ, the equivalent, or total resistance, over 1 is equal to 1 over 0.29545. And again, I know there's a lot of decimal spots, but you know that Quest gets cranky if you don't round right. Okay, last step is REQ divided by 1 is just REQ, right? Because it's anything divided by itself is itself. Is equal to, alright, type that in your calculator. 1 divided by 0.29545. When you do that, I got 3.3846 ohms. And again, I know I don't normally write that many decimal spots, but I think Quest is going to look for that, particularly because it's kind of a smaller number for that resistance. So we've got our answer here, 3.3846. 38. Okay, great. I'm going to fill that in on my verb chart. I know there's a lot of work to get that, but again, parallel circuits are just a little more annoying. 3.38. Yeah, that's all I can fit. Alright, I'm going to erase a lot of this math, and then we'll try the next part. Alright, question 4. What is the potential difference across the source? Again, that source, they're just referring to the battery. So what we're finding is potential difference, just another word for voltage. Oh no, I erased everything. Oh, sorry, I gotta fix that. Okay, sorry about that. So we want the potential difference across the source. Again, that's the voltage, because potential difference is just another word for voltage. And the source means the total, or that battery. This is a great example of like of how to use a verb chart, because there's no real way to get there. We're missing a lot of information about the circuit as a whole. I don't know. So let's just find like anything, like something that we can find, and even if we don't know how it's going to help, you know, at least we'll know more. So I'm looking at this row right here. This one with this one right here with R2 in it. Because you see how we know the resistance and the current? I think that's all we need to find is voltage. And again, if you don't know why that's going to help right away, let's just find something. That's kind of what these problems come down to, is just find anything and then take it from there. So R equals V over I. Again, you gotta stay within your row when you do these tables here. So I'm going to stay in this row right here. We know the resistance is 12. We know the current is 5. So 12 equals V over 5. When you multiply across, you get V is equal to, I think, 60 volts. So I'm going to fill this in here. 60 volts. Cool. I didn't write in something else. Let's lose that. So, great. And again, now we just gotta like find something. Where can we go from here? Well, it's a parallel circuit, and that voltage is really helpful in a parallel circuit because, to consult our reference table rules, in a parallel circuit, it looks like the voltage is the same through all the devices. So if it's 60 through this device, then it should be 60 through this one, and it should be 60 through this one, and it should be 60 in the total supplied by the battery. And I think that's actually what our question was asking, right? Was the total voltage supplied by the battery here. So we're all done. The answer was 60 volts. Alright, let's find the current in the 22 ohm resistor. Alright, our table is pretty well filled at this point, so we don't have to like really work too hard to figure this one out here. Well, the current in the 22 ohm resistor, that's this row, it's that top row, and it looks like we know V, we know R, and I can find the current using V and R using R equals V over I. So these circuit problems, they get a little repetitive after a while, but that's what we're doing. Whoops, sorry. 22 equals 60 over I. Cross multiply carefully. You should get a value. I think it's a little less than 3, but I gotta do it in my calculator. And what I got was 2.727 amps. I'm going to fill that in on my table here. So again, that was, I think we did the 22 ohm resistor, so 2.727. And that was the answer to this question, right? 2.727 amps. It's a decimal. Alright, calculate the current for the 6 ohm resistor. Alright, now we're in this row, right? The 6 ohm resistor row. And again, we know R, we know V, solving for I. So R equals V over I. We know R. We know V. Solving for I. Cross multiply carefully again. You should get 60 divided by 6, which gives you 10 amps. Throw that in up here in my table. And that's the answer to the question, right? That's what we were looking for. Cool. So again, just verb chart. Same strategy. We've been doing this for a little while. Just a different set of rules. I'll clear this out, and then we'll try question 7. But if you've been following along, try question 7, 7, 8, 9. Try it on your own, and then use this as like a sort of a backup. So give it a shot on your own before I run through it. Alright. Last up, 2 resistors, 14 ohms and 2.7 ohms are connected in parallel across the 24 volt battery. Find the potential difference across each resistor. Great, sounds like we're doing circuit analysis, right? And we know what to do for that. I'm going to draw a picture, and then I'm going to do a verb chart. I'm going to draw my picture, draw my picture sideways, just to show you guys something different. So we've got a 14 ohm resistor, a 2.7 ohm resistor across a 24 volt battery. I think we've only got 2 devices, and then we've got the total, meaning the circuit as a whole. And just, oh god, oh no, come on. And just like always, we're going to, just like always, we're going to just fill in everything that we know, and then we will take it from there. Let's go through it. Alright, we want we've got a 14 ohm resistor, so I think that's 14 ohms. we've got a 2.7 ohm resistor, so this is 2.7, and then we've got a 24 volt battery. Alright, and I think that's all we know, so let's go. We want the potential difference across each resistor. Remember, potential difference is just another word for voltage. Gotta remember that. Alright, so we want the potential difference across each resistor. That's like these guys. Boy, I forgot my circuit rules. I think I'm just going to double check them in my reference tables. And, oh man, it looks like the voltage is the same across all of the resistors. So that means that this one should be 24. That means that this one should be 24. And it means that our answer should be 24. So there's not a lot to this question if you know what you're looking for. The voltage is the same for every device in a parallel circuit. There we go. 8. Find the current in the first resistor. Okay, so the first resistor that they mentioned, I think, was the 14 ohm. So we're going to find the current in the 14 ohm resistor. On our verb chart, that's this guy right here, this box. Alright, so we know R, we know V, solving for I. You know, I'm hoping that this feels repetitive at this point, because that means you're used to it and you know what you're doing. So we've got a resistance of 14, a voltage of 24, and then we're solving for I. 24 divided by 14 is... I don't know how to do that. I got 1.714. 1.714 amps the unit. So I'm going to fill that in. 1.714. Yeah, I know. It's a little messy. And that's our answer. 1.714. Cool. Alright, question 9. Find the current in the circuit. This is another good example of why we need a verb chart. So we want the current, which is I, and we want it in the circuit. That's going to be this box right here. And we really don't have any direct way of getting it. So there's a couple different options here. One thing that we could do is, well, if we knew this resistance, we could do Ohm's law. But then we'd have to do that 1 over equation. And I hate that. I don't love it. So I'm not going to do that. I'm just going to find this guy right here. I'm going to find the current through the other resistor. And I'm just going to do that to, again, the more we know about this current row, the closer we'll be to figuring out what we have to know. They are not all going to be that 1.714 though. The currents are not all the same. That was a property, if you remember, of series circuits, which this is not. For this circuit, they all add up to the total. It's a parallel circuit. But that's why I'm going to find this value right here. Because if I know the first one and the second one, I can definitely find it out what they add up to. So that's what I'm going to do here. I'm going to do Ohm's law. R equals V over I. And I'm going to do it for this middle row. So you've got a resistance of 2.7 ohms. We've got a voltage of 24 volts. And let's find out what the... I got a current of 8.8 repeating. So this is 8.88. But again, that's not what we're looking for. We're looking for this one down here. And if you're wondering how to get from this and this into that total current, let's go back to our reference tables. Boy, those sure are handy. We've got the total current. The total current is equal to the first one plus the second one. This is getting really messy. Plus the third one plus the fourth one and so on. So what we can do is we can just add up those two individual currents to get the total. That's what I'm going to do. When you add these two together, again, I'm filling out that box right here. 1.714 plus 8.88 is equal to, I got about 10.6. And that's what we were looking for, right? So 10.6. Oh no. I got 10.6 amps down here. Let's get rid of all that. And that's it. Now, if you did it the other way, meaning if you found the equivalent resistance and then did Ohm's law for this bottom row, you should have gotten the same answer. So if you tried that but didn't quite get there, just double check your work, particularly that 1 over REQ equation. And that's it. Hopefully this helped. Yeah, that's it. Got myself.